All right, let's do some circuits problems, hopefully in an efficient way. So here's a very simple circuit, one resistor. I'll then get to series, and after that, of course, parallel. So reflect back on these to help yourself out, but the first idea with this is I can apply actually the voltage rule, or the loop rule, I'll call it, where if there's only one resistor, the voltage from the battery essentially needs to get lost across that. You can write negative 6 volts. I'll keep it as positive for your guys' sake with the math, excuse me. But once I essentially know the voltage across resistor 1 and its resistance, I can then apply Ohm's law that says 6 volts equals the current through resistor 1 times 2 ohms. So of course when I divide those, solve it out, I get that the current through resistor 1 equals 3 amps. Alright, so that's going to at least be, I guess, kind of our reference point, is that when I just had resistor 1 of 2 ohms and the battery of 6 volts, I got a current of 3 amps. So we hopefully learned in the lab conceptually that if you add more resistors in series, that it actually should increase the total resistance, which you see I already have the equation set up right here. So let's solve for this. This is kind of a no-brainer. I've got the 2 ohm resistor, but I'm adding the 1 ohm as well. And that gives me a total resistance of 3 ohms. So that's pretty clear as day with the math. But then we learn conceptually that if I increase the total resistance, the total current should decrease. So it should be less than 3. So I should be able to apply Ohm's law with the total values right here. So total voltage of 6 volts equals the total current times the total resistance. So when I solve this out, I get a total current of 2 amps. Which again, we said that if we add more resistors in series, it should increase the total resistance, which should decrease from the original value up here, which should decrease the total current. So I like that conceptual understanding. That connects very well with the math. In terms of then being able to solve for the current and voltage across these, which with a quick reminder, the loop rule basically says in a loop, and it relates to voltage, in one loop, the voltage given by a battery, alright, the pressure buildup should be lost across the resistors. If I only cross one, then it loses all of the pressure or voltage. This one, I wish I could apply the same idea, but there's 2 resistors, and they're not the same resistance, so I don't know if that splits evenly. So there's another idea, which has to do with the current, that basically says in a series circuit, the current stays the same. Since there's only one path, alright, the current should then, I shouldn't draw a loop, sorry. The current then should be the same for each resistor. So the total was 2 amps, so it's got to stay the same, because again, there's only one path, and it's like water flowing in a river, it shouldn't split up. Then if I organize my information, I can see that I actually know 2 out of the 3 unknowns for Ohm's law, so I should be able to solve for the voltage across resistor 1. The current through it is 2 amps. The resistance is 2 ohms, so the voltage drop across resistor 1 is 4 volts. And the voltage drop across resistor 2, current is 2 amps still in a series circuit, and now this resistance is 1 ohm, is 2 volts. I feel good about these answers because that whole loop rule with voltage basically says in one loop, now I can draw the loop, in one loop, whatever resistors I go across, they better take all this voltage. So it loses 4 volts across the first, so then it must lose the remaining 2 out of the 6 across the second. So that's real good right there. Okay? Big idea again was basically you add resistors in a series circuit and it's going to decrease the current. That is literally kind of the main idea for series connections in terms of electronic devices or home appliances or even your house. If you have a device that doesn't want a certain amount of current and it's getting maybe too much current, you can add resistors, not always light bulbs, but resistors in series, and that'll drop the current down. So take it from 3 to 2. If you want to drop it a little bit more, you could add a larger resistor or another resistor in series. Okay? All right, last part real quick, the parallel circuit. This is the opposite idea. Okay, so this one, what's really weird is actually think of pathways. If you add more resistors, you're making more pathways. which actually makes it easier for the charge to flow and is less resistance. So if we solve this one out real quick, I'll try to be quick. Basically, I'm just going to plug it into the inverse equation. Lowest common denominator for these is 2. So I can multiply this 1 over 1 times 2 and this times 2. That becomes 2 over 2. Add the numerator, you get 3. Denominator stays 2 ohms. But remember, I've got to flip it. So I know I'm not really showing a lot of the math here, but the total resistance ends up being 2/3 ohms. All right. Going back from the beginning, it does actually kind of show the total resistance decreasing, because if I just had the 2 ohm resistor up here by itself, the total resistance was 2 ohms. When I then added another one on top of the 2 ohm in parallel, it actually decreased the total resistance. What does this then do ultimately? It actually then, if I add this information over here, let's organize this on the battery. Alright, I can then use Ohm's law to solve for the total current. And if I plug in that into Ohm's law, the total voltage is 6 volts. Solving for the total current, and the total resistance is 2/3 ohms. Of course, I divide by the fraction. Dividing by a fraction is the same thing as multiplying by its reciprocal, so I've got 3 times 6 is 18. Divided by 2 is 9. So the total current is 9. And that again agrees with the idea that, well, I had an original current with just the 2 ohm resistor of 3 amps. If I actually add more resistors in parallel, the total current is going to go up, because it's not only got to supply the current that was originally going through this 2 ohm resistor, but it's got to now add even more current for this second path. Because if you recall, the light bulb's brightness actually stayed the same. Alright, so I've got a total current. What's different though in this circuit is that the current at this junction right here, we call it, will split up. So it'll basically go from the total value of 9 amps and then split up individual paths. Call this current 1, this current 2. Okay? I don't know how they split up. Definitely not even, because these are different resistances on each path. So what I would probably do first is try to figure out the voltage. Again, based on the loop rule, if I just take a single path, let's say the inside path, I only go across this light bulb, so this must lose the total 6 volts. Same idea applies if I take the outside path out here, is that I only went through this light bulb, so that must lose 6 volts as well. Seems kind of weird, because you're like, wait, this already took the 6 volts that the battery had, but again, think of water flowing down a mountain. The water at the top of the mountain has the same potential to fall, and it can take different paths. So that's how I understand it best with kind of water flowing down a mountain analogy. Anyway, once I have these, you can clearly see that I can solve for the current again with Ohm's law, but I'm going to solve not for the total, but current 1 using the resistor 1, 2 ohms, and I get a individual current of 3 amps, which actually is great to see, because without this resistor, this was the original 3 amps that was flowing when it was just the 2 ohm resistor, which I called resistor 1. So that is why the bulb brightness stayed the same. It's actually receiving the same change in voltage and current through it. Why the total got bigger though, altogether, the total, is because it's got to apply that original 3 amps, but now apply even more to this outside one. So Ohm's law one more time, 6 volts equals now the current down path 2. That resistance is much less, so I'm going to guess that it gets more current, and when I solve that, it gets 6 amps. I also like seeing this because if I think about the currents on the individual paths, 3 and 6, that is equaling up to the total I started with, the 9 amps. All right. So the good news is basically is we can add more paths, which is kind of like more rooms in a house, more devices that are also independent of one another. If I cut the current here, it still runs out here. The downside to this, though, with the drawing more total current, is it drains the battery quicker. So parallel is pretty cool because it's like, well, hey, if it's still drawing 3 amps from this, why not have another room that can light something up or turn something on? That's awesome. It'll just drain the battery a little bit quicker. So a lot of pros and cons to these. Hopefully this helped out, though, to make it a little bit more efficient and understandable, and you can look back on. All right.